So the ideal gas law, topic for this section. We've discussed three relationships that we refer to as simple gas laws. Those are the relationships between, come on, pointer. No pointer? Come on, there we go. Volume and pressure, volume and temperature, volume and amount of gas in moles. If we combine those, we can say that the volume is proportional to N times T over P. Because the volume is proportional to 1 over P, directly to T, directly to N. And so we can have this proportionality. If something is proportional, that means it's equal to some constant times that. So the volume is equal to nRT over P. R here is the constant that makes that an equality instead of just a proportionality. And if we bring the P up so that we get rid of the fractions, we get this PV equals nRT, and that's what we refer to as the ideal gas law. Sometimes called Pivnert. R is a constant, and it's referred to as the ideal gas constant. The value of it depends on the units that are used. Just like if you measure the length of a piece of paper, the number depends on whether you're using inches or centimeters. So the value of R depends on the units that are being used. So typically we'll use atmospheres for pressure and liters for volume, and then R will have the units liters times atmospheres over moles times Kelvin, which seems like a really messy set of units. But if we take PV equals nRT and solve for R is going to be equal to PV over NT, right? And if volume is liters and pressure is atmospheres, N is moles, temperature is always Kelvin, that's where the units come from. So it's 0.08206 liter atmospheres per mole Kelvin. You'll save yourself some time if you memorize that. This is just a graphic from your textbook showing how the different laws, Boyle's, Charles, and Avogadro's law, come from the ideal gas law. So for Boyle's law, we're keeping N and T constant, so they're not changing. So N and T can get lumped in with the proportionality constant, and you've got volume is proportional to 1 over P. And similar for Charles' law and Avogadro's law. For those of you that enjoy proofs in mathematics, you'll appreciate this. If you don't like it, it's okay. You don't have to know it that way. So let's do an example. An 8.5 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? So we could take the approach of making a table, or we can just label things as we come across them. I'm going to pretend I don't know this is an ideal gas law problem, and I'm just going to start making a table. So remember, we got row 1 and row 2. So I come across 8.50 liters, and that is a volume. I know that because of the unit. Liter is a unit of volume. Contains 0.552 moles. 0.552 moles of gas. The letter for that is N, amount of gas in moles. And I keep going on, and I get 305 Kelvin. And that's going to be a temperature. Is that an okay unit to use for gas law? Yeah, that's the unit we do need. And now I realize I've run out of numbers, and I have nothing to put in this second row. That's because there's nothing changing. The simple gas laws looked at, well, here's this volume and temperature, and then we changed one of them. How did the other one change? In an ideal gas law problem, you just have one set of conditions. So making the table is not a wasted effort, because we have now collected and labeled all of our numbers. We just don't need that second row. So here's my volume, here's my N, here's my T. What are they asking me for? Pressure. So I need the ideal gas law. PV equals nRT. And they're asking me for the pressure. So I'm going to rearrange this. I'm going to divide both sides by V. The pressure is equal to nRT over V. So I have V, N, and T. I know what R is, and so I can just plug all of these into this equation. Always write the units. 0.552 moles. The ideal gas constant is 0.08206 liters times atmospheres divided by moles times Kelvin. The temperature, 305 Kelvin. And then all of that's going to be divided by the volume, 8.50 liters. Before I do any math, I want to check my units, because sometimes we try to trick you with the units. So here I've got a liter in the denominator and a liter in the numerator. Those are going to cancel out. So now in terms of units, I only have what's on the top. Here I've got moles, and in the bottom of this fraction is moles. The moles cancel out. And here I've got Kelvin, and those cancel out. If my volume was in milliliters, then the units wouldn't work out, and I'd have to do some converting. But all my units worked out. I got one unit left. It's a pressure unit. So 0.552 times 0.08206 times 305 divided by 8.5. How many significant figures should this result have? 3? Yeah, all of these have 3. So my answer should have 3. So I'm going to write down the first 3, 1.62, and that's 3, and add 2 more. And then I'm going to round that. 1.63 atmospheres is the pressure. Any questions? Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So I read this problem and I recognize, okay, I don't have something changing, so I don't really need to make a table. This time I'm just going to identify these different variables. So I'm still writing down the numbers, always collecting the numbers, and then figuring out what to do with them. So I have 0.556 moles of gas. In PV equals nRT, that's N. So that's my N. And I'm told that the pressure, P, equals 715 millimeters of mercury. I just realized I forgot a step in that last problem. It also asked for the pressure in PSI. I forgot that. Oops. And I'm going to go back, because my app here won't let me do that. Oh well. 715 millimeters mercury, temperature equals 58 degrees Celsius. Is degrees Celsius an okay unit to use for the temperature? No, it's not. We need to convert that to Celsius. I'm sorry, to Kelvin. So we're going to add 273. And that'll be 331 Kelvin. I'm just going to go ahead and write down what R is. R is 0.08206. It's the ideal gas constant, and so it's always the same. Isn't that nice? Liters times atmospheres over moles times Kelvin. If I look at the units on the ideal gas constant, that tells me what units I need to put everything else in. So here I've got moles and I've got Kelvin, but the millimeters of mercury isn't going to work out because this constant has atmospheres in it. So I need to convert millimeters of mercury to atmospheres. All pressure unit conversions can be done in one step. So I want atmospheres. I'm going to put millimeters of mercury in the denominator. Those are going to cancel out. 1 atmosphere is exactly equal to 760 millimeters of mercury. You should memorize that one because we're going to use it a lot. So 715 over 760. That would have 3 significant figures, but I definitely want to carry 2 extras because this is not a final result. So 0.94078 atmospheres. That's my pressure. So I'm asked to find volume. So I've got PV equals nRT. I want to rearrange this for volume. So I'm going to divide by pressure on both sides. Volume is nRT over P. So volume is nRT divided by P. And I've got all my things labeled there. 0.556 moles. Got R. Kelvin. Don't know what happened there. And I'm dividing by the pressure 0.94078 atmospheres. I've underlined that third significant figure there to remind myself that the pressure had 3 sig figs. Before I do any math, I'm going to check the units. The moles cancel. The kelvins cancel, the atmospheres cancel, and I'm left with liters. .556 times 0.08206 times 331 divided by 0.94078 equals. By the way, this ideal gas constant is not an exact number. That's got 4 sig figs. But the rest of my numbers all have 3, and so my answer should have 3. 16.052. The unit is liters. If you struggle with significant figures, 3 or 4 sig figs is usually a good number. Sig figs are important, but they are not the most important thing in chemistry. 16.1 liters is the volume. Any questions? It's an ideal gas law calculation.